Perfect. As you know, my name is Samuel Obara. I teach here at Texas State. I've been here since 2006. Now, according to my presentation here, is that, let me see here, just a minute. I guess, just a second here. Let me unshare here quickly, because it doesn't really show when I share it. It does not show the title of the presentation for some reason. Let me see here. Let me try to share again. It does not. Maybe I will just put it not on a presentation mode because it was not showing that, right? Okay. Now, with that said, so what is the role of technology in learning of mathematics? Let me give you a very brief, background about this project. This is an NSF project. We were fortunate to get about close to 3 million NSF grants, and it ran from 2012 from 2014 to 2018, around there. So this project was basically trying to see a way that were, high school teachers in Texas to be encouraged to introduce technology in their instructional practices. So there's research is out there, especially in Texas, is that the most exams that are set here in Texas, they basically focus on algebra. Nothing is, geometry is not emphasized much. Therefore, you can find, teachers coming to college without having very minimal experience with technology. So as we have been getting, teachers coming, especially pre-service teachers coming to our college, we have been seeing these gaps. And then we made a case to NSF, and that's how we were funded about this project here. So here is the National Council of Teachers Mathematics position. It says that it is essential that teachers and students have regular access to technology that support advanced mathematical sense making, reasoning, problem solving, and communication. Effective teachers optimize the potential of technology to develop student understanding, stimulate their interest, and increase their proficiency in mathematics. When teachers use technology strategically, that's the point there. And this was basically the core idea about our research project. Strategically, not just using it for demonstration, but strategically, they can provide great access to mathematics for all students, not to some students, but to all students. So that was basically the core of our project while we were running this research project here. So some few things here I'd like also to point out here. It says that simply having access, and here, this is the key point here, simply having access to technology is not sufficient. Most teachers, when they know they have technology at their thing, exposed to them, but having is not sufficient. Teachers and the curriculum play a critical role in mediating the use of technology to enhance mathematical learning. And that is basically what it was. So when we were running this research project, we carried out a survey of teachers, especially using the dynamic software. How do they have it? A number of times it said, yes, we do have it. Now, how do you use it? Then it became a problem. So we ran this project here. Now, before I do that, I'd like to point out some few things here that are basically the integral piece of our projects. So when we talk about dynamic geometry, what do we really mean? So I can say, well, if I draw a triangle, I can change it around, change the angles, change the lengths without really redrawing the triangle again. So the student can easily be able to see several dimensions of that triangle dynamically. And therefore, that is quite different from using, a compass and straight edge, where you just construct something and it is what? It is static. You can't move. You cannot be able to, change and see what is the relationship between the length the area, and all that kind of thing really that the student really likes. So DG over tools for constructing dynamic diagrams on the screen of the computer. If the constructions has been done by using geometry properties, those properties and all the driving properties are preserved when dragging and the element of the diagram. So that's the key here. So if I draw a triangle and I move it around, it still remains to be a triangle. The shape may change, but it still remains to be a triangle. The question is, what can we learn? Either as you move it around, there are a number of things that changes. It still remains to be a triangle. That's basically what we have here. Now, the major ingredients of this is the dragging aspect. Click and drag. You know, when you are in your desktop, you can move files around. You click and drag them around. So that's basically the feature that we use here. It's an essential feature of dynamic geometry. Over visualization of phenomena ruled by mathematical laws. Represent of mathematical objects behaving mathematically, and finally mathematical becomes tangible. Student can easily be able to say, okay, well, this triangle, when it was here, and when we changed it around, it looks like, you know, maybe there are things that are changing, others are constant, right? See. So for example, I can say, okay, I have a triangle, I'm preserving my height. I can construct a triangle in such a way that I cannot change the height, but I can be able to change everything. So students can see, okay, it looks like maybe the shape of the triangle is changing, but the height and the base are the same, therefore the area is the same. So students can start drawing conjectures, and therefore they can be able to own the math other than just cramming and moving on in that aspect. So that was the main thing here. Now, so we ran a summer institute here, and that's basically what I want to share with you here, what we did during the summer institute. And remember, these are high school teachers, pre-service teacher having a vast experience. So as part of the project, teachers were involved in a year-long professional development using dynamic geometry software to engage in-service teachers in extracting mathematical idea. That's the key thing, extracting mathematical ideas through the process of experimentation, observation, data recalling, conjecture testing, and proving results, right? So one important thing that I like maybe to add here is this concept of proving results. You know, the concept, most teachers that who we worked with, they could be able to do a number, but when it came to proofs, it was a problem. Now, when we were making our case about this, then we said, okay, if our, if our in-service teachers with a, experience in teaching are not comfortable in some, in some proofs, then it means therefore that students will never be exposed to do this, because if teachers cannot understand a proof, then it means therefore that, students will not have that experience. So because of that, then we had this activity that which we did what? We worked with the teachers, and maybe I may want to engage you guys a little bit here. So I'd like you to visualize this. This is a very simple problem. Here, I don't know, okay. Let's see here. Oh, it's a very simple problem here. Let me move some of the things here. Now here it is. It says here, construct what? Construct an arbitrary triangle just on your piece of paper. Maybe you can do it. Construct an arbitrary triangle such that the point D, E, and F respectively are sides, B, C, C, A, and AB, right? And then you have the, DB is a third of BC. CE is a third of CA. AF is a third of BC, of AB, sorry. PQF is formed by what? By constructing the line segments AD, BE, and CF. What is the relationship between PQR and ABC, right? So that's basically what you can see down here. Maybe if I can be able, let me move this one up here. So that's what you can see here. So you can see we gave them this triangle here. So the main goal of this project was, does technology really make the difference in terms of exposing teachers to the what? To the proof aspect of anything? Does it really help them? So we asked them to have this. So you can see it's A, F, A, you have, this is a third of that, this is a third of that, and that is a third of that. Then when we did, we just basically connected this. We connected this, right? And this triangle here was created, right? Now the question is, what's the relationship between this triangle here in reference to the rest of the triangle? Can somebody make a guess? Unknown caller. Can somebody make a guess? Those are some of the conjectures the teachers did. What do you think will be the relationship between this and the whole triangle? Is it a half? Is it a quarter? Is it a one? What is it? So the teachers, we gave them the opportunity to do that, right? So they made a conjecture, which is basically an educated guess, and then we exposed them. Okay, now do what? If that's the case, can you then be able to use technology to see how far you are in terms of your educated guess, right? See, so let's see here. Okay, so this is basically what you have here. Now let me move here. Okay. This okay. So let's see here. Yeah, okay. And now then this teacher here that which you can see here, maybe let me see if this will work. Yes. So this was one of our participants. And then this teacher here constructed this. And what she did was, she said, okay, she said, okay, the relationship between this, then she counted, maybe this is maybe the same as that, and this will make one. So he said, is it 1, 2, 3, 4? So then he said, maybe it's 1/5, right? Based on this, right? But now, then she went ahead and then used the technology here, the software which we are using. Then the software can be able to construct the area of this and be able to come up with what? With the relationships. So when she did, then you can see here, when she took the ratio between this triangle here with the rest of the triangle, the area came to be what? To be 7, which means therefore this is 1/7 of the whole triangle, right? 1/7 of the whole triangle. Now the question here is, I mean, it was not the same as what she had conjectured, but at least it gave her an idea of what is going on. Now let's see what happens here. Now with that said, she started making proofs here. So I'm not going to share much about this proof here, but I would like to share with you what we found out, right? So the teacher, this teacher here, I mean, especially with our guidance, she came up with a long proof here that which basically is a long one here, but finally she came up with what? With the final results. So what are the discussion here that I would like to point out here? One point here is that things that which we can think about moving forward is that simulating by constructing mathematical ideas through exploring, conjecturing, teachers may be able to come up with their own ideas for the proof. Those are some of the things, some of the findings that which we came up out of this project. Another thing that which we came up with is the number of research studies indicated that engaging teachers, strong students, students, teachers, right, in the face of preceding proofs did not necessarily lead them to an awareness of the need of a proof. On the contrary, here is the point. In the present study, we found that the dynamic geometry software and appropriate questions prompted and /or motivated teachers to seek justification for their conjectures. So that was the key thing that which we noticed. Even those that really didn't care about coming up with a proof, they said, okay, I see something here. Maybe, let me see, it looks like this is what it gives them an idea. It gives them a motivation to kind of think about it and have that motivation of the need of a proof coming forward. And that was one thing that really we came up with based on our research. The third one is during the proof phase, 2 of the 3 teachers in this study justified their conjectures for the problem based on the screening output. That was the key. You see, with the technology, you can be able to justify. You can justify, okay, it looks like, right, based on what I have here, this software, by taking ratios, I can see, okay, it looks like is 1/7, right? Is 1/7. Oh, so therefore, if that is the case, then it means therefore that at least you have the first step of starting a proof. Those are some of the things that which we looked at. The next one that which we also looked at was, for this purpose, the measurement facility, and this was key. For this purpose, the measurement of facilities of the software provide the means of finding explanation and the means for gathering information for justifying their results, right? Finally, I can say here, finally, we can say, let me, yeah, okay. And finally, you can say the measurement also provides students with specific examples that formed the basis of further conjecture and generalization. See, so that's why in this study we will really emphasize the concept of doing what, of using dynamic software, and the teachers who have been really encouraged. Now, since this project ended, we have visited the site a number of times, and we have seen how teachers are basically engaging with their students, and a number of things that really we have been motivated the way they were done. Because this study we did, some teachers used technology and others used basically paper and construction tools like compass and straight edge, and we could see very distinction differences between those teachers. Right. So that's the end of my presentation.